This is going to be a very special program. We are concentrating upon the high altitude observatories on Mauna Kea, the extinct volcano in Hawaii. I mean, we hope it's extinct. Up there, some of the world's best astronomical telescopes, and Chris is there. Down here, I'll be talking to some of the astronomers who use them. So, first of all, over to Chris in Hawaii.
Welcome to the summit of Mauna Kea, the highest mountain in the world. Sacred to the native Hawaiian people, it's also the closest astronomers come to our holy site. The 13 telescopes up here study the universe in wavelengths from optical through to the radio, and look at everything from star formation to distant galaxies, and from supernova to extrasolar planets. The results are incredible. Choosing different wavelengths means tuning into environments at different temperatures and seeing different parts of the universe. Both gamma and X-rays, along with most of the ultraviolet, will be blocked by the atmosphere, but Keck, working in the optical, will see things very differently from the UK infrared telescope. UKERT's view, on the other hand, will be different again from the cold and dusty universe seen by the James Clerk Maxwell telescope in the submillimeter. Mauna Kea is classed as a dormant volcano, and it's impossible to ignore the signs of activity, from the beautiful coloured soil to the cinder cones which pepper the side of the mountain behind me, each one marking the site of a previously active vent. Despite the volcanoes, being smack in the middle of a large Pacific island has several advantages. The atmosphere above us is extremely dry, vital for many observations. In addition, the cloud tends to stay down below in what's known as the inversion layer, leaving the summit nice and clear with stable seeing conditions. Opened in 1979, for 13 years the largest mirror on the mountain belonged to the United Kingdom Infrared Telescope, or UKERT. Recently updated, it's still the largest telescope anywhere in the world dedicated to these wavelengths. UKERT owes its success to its superb mirror, good enough for optical astronomy, let alone the dark and dusty infrared. It's this, together with a succession of new instruments, that have kept it at the cutting edge of infrared astronomy for so long. The latest instrument, WIFCAM, the wide field camera, is the large black cannon attached to the telescope behind me, and there's nothing like it anywhere in the world. Tonight, the new camera is being treated to a tour around several parts of the sky that should be familiar to observers back in the UK. Here to set up for tonight's run is Dr. Andy Adamson, Director of UKERT. So we're in front of UKERT, but why the infrared anyway?
Well, if you asked me that question 25 years ago, you'd get a different answer from now. I suppose when UKERT was first built, it was a really pioneering telescope, and infrared astronomy was very much in its infancy. The reasons for infrared now, I suppose, are twofold. One is that the universe is expanding, and so the very distant targets which are needed to look at for cosmological reasons tend to be at very large redshifts. When we talk about more nearby things, in our own galaxy for example, the star formation that goes on is all enshrouded in dust. You don't see much of this in the visible light, and you do see it in the infrared, and that's a very key driver for infrared astronomy. We also see through dust very well. So for example, we see through to the centre of our own galaxy in a way that you just cannot do in visible light at all.
Funded by the UK Research Council, PPARC, British scientists get the chance to play with this fabulous instrument. Dr. Sandy Leggett and Dr. Chris Davis are resident astronomers here, coordinating observations as well as carrying out their own research.
One of the great advantages of observing in the infrared, especially for star formation, is that it allows us to peer deep inside dark molecular clouds where young stars are actually being formed.
And we've got some wonderful examples of that, like the Chicken Nebula.
Yeah, the Chicken's a nice example. This is a high mass star forming region we've been studying at UKERT. And again, if you look at an optical image of this region, all you see is the very brightest stars. But in the infrared, obviously, we can peer inside the cloud and see all this wonderful structure.
And a wonderful image of our nearest large star-forming region, Orion.
With our new wide-field camera, WIFCAM, Orion was one of our first targets, and WIFCAM has revealed fabulous structure over a huge area. Not just the young stars, but also a lot of dynamical processes, outflows. These are remarkable phenomenon associated with young stars. Basically what's happening is As the star is forming, material is spiralling down through a flattened disk, what we call an accretion disk, so gas is accreting onto the star, and as it gets closer and closer to the star it gets faster and faster. So to slow the spiraling down, the object actually produces outflows, and these are remarkable jets of gas from the poles of the star, travelling at hundreds of kilometres per second, extending over millions of kilometres across space.
And so we've talked about star formation, but Sandy, you've been looking at small stars.
Well, brown dwarfs are between a star and a planet in terms of temperature and mass. They're actually too cold and they don't have sufficient mass to ignite hydrogen nuclear fusion in their core, so they don't shine like stars. But they start off very hot when they're formed out of the molecular gas, so they can still shine for up to 1 billion years.
And you, Kurt, played a crucial role in their discovery.
Oh yes, we were looking for brown dwarfs for decades, from the 70s and the 80s, and finally in 1995 one example was found at Palomar as a companion to a red dwarf. And we kept looking, we still only had this one example. And in 1999 we found the second example of what are now called T-dwarfs, and I observed this just sitting right here. It was 3 o'clock in the morning, just me and the telescope operator, and I just wanted to tell everybody. You know, it was so exciting, it was terrific.
And so the first brown dwarf was found. Splitting its light up and looking at its spectrum, it's obvious that it's more like a planet, here's Saturn's spectrum, than a star, shown in red. But there's a missing link. Is there anything that has a spectrum intermediate between a star and a brown dwarf?
A year later, in 2000, on one night we found 3 or 4 objects which filled in the gap. It was an entire spectral sequence. For the first time it was like a real population, and I think that was my best night at any telescope ever, and I can't imagine having another night like that. It was just really, really exciting.
As the sun sets down into the cloud, it's a race against time to get the telescopes ready for science as soon as possible. Andy and tonight's telescope operator Thor have things well under control. The telescope is working well and data is already coming in. Well, it's a clear night outside, and what are we looking at?
Well, right now we're in the middle of an observation of M33, which is a large spiral galaxy. With previous instrumentation, it would have taken many years to build up an image of this galaxy because it's so large on the sky.
This is the optical image.
This is the optical image on the sky survey. And the 4 patches that you're seeing here are the 4 WIFCAM detectors, each of which is separated by a certain distance, as you can see. And what we're doing is to build up a completely covered area around this target, so that we get a complete image of the entire galaxy.
And this is live data coming through?
Yeah, so each of these 4 detectors produces a stream of data that comes in, and each of these is showing you both the data that are on their way in, so we have a live frame coming in each time we get an update, and here is the latest stacked image. So up here is the nucleus of the galaxy, and this is out into the disk. So again, you can see that the galaxy is quite large, and we don't see the whole thing in one chip.
The images from WIFCAM are certainly impressive, and it's only been operating for a few short months. With plenty more clear nights to come, we'll be hearing a lot more from you, Kurt. Down below the ridge on which you, Kurt, sits lies Submillimeter Valley and the JCMT, or James Clerk Maxwell Telescope. Unlike the telescopes up here, it can happily observe during the day and owes its unique appearance to the world's largest piece of Gore-Tex, a windshield that happens to be invisible in the submillimeter. So Gary, what is the submillimeter?
Well, Chris, the submillimeter is really just another form of light, and there are actually many different types of light, and you'll be familiar with optical light, which we see with our eyes, with X-rays, with radio waves, and of course with the infrared, which is used at UCURT. These are all just different types of light. It's just that the human eye is only sensitive to visible light, which is only a small part. Well, with the JCMT, we study the submillimeter, which is yet another form of light. And submillimeter comes from objects in the sky which are cold. So, roughly, we're measuring the heat signatures of objects in the sky which are cold.
How cold?
Well, really cold, actually. We're talking temperatures less than 50 Kelvin or so. So that's within 50 Kelvin of absolute zero. So when I say heat signature of cold objects, it's a bit oxymoronic, but that is actually what we're trying to do.
But what sort of things do you see?
Oh, well, actually most of the material in the universe is cold, and that's quite surprising. But to give you a few examples, the interstellar medium between stars in the galaxy is not empty space. It's absolutely full of stuff. It's full of molecules in the gas form, and there are a lot of dust particles as well, and we can measure both of these things using different type of instruments on this telescope. And the great thing about submillimeter astronomy, which of course I should have mentioned at the beginning, is that we use submillimeter astronomy to study these origins questions. How do stars form? How do galaxies form? And how do planetary systems form?
The big questions.
These are the big questions of modern astronomy, absolutely.
The telescope looks rather like a radio dish, but it's not. It's a mirror. Because the wavelength of the light we're using is much shorter, the mirror must be smoother. Now the light comes in through the windshield, hits the mirror, goes up to the secondary, and is reflected down through the hole into the receiver cabin, which looks rather like the TARDIS. And it feels like the TARDIS as well, crowded with instruments. This tertiary mirror here selects which one is going to be used, and therefore which wavelength we can monitor the sky in. The instruments can only work at extremely low temperatures in order to prevent their background noise overwhelming the tiny signals from space. As the instrument is cooled using liquid gas, normally nitrogen or helium, the atoms inside slow down. The ultimate would be to reach absolute zero, minus 273 degrees centigrade, when the atoms have no kinetic energy at all, when they're completely stopped. That's impossible in practice, but one instrument gets very close indeed. This is SCUBA, now retired from 8 years hard work on the telescope. When it was running, the detector chamber was cooled to just 100 millikelvin, making it the largest known volume in the universe to be that cold. Before it came along, we had to map the submillimeter sky 1 pixel at a time, but SCUBA is a camera, and the images it produced were revolutionary, showing us new details from everything from new solar systems to distant galaxies. So, you've been using the JCMT, and what have you been working on?
Well, my interest is in planetary systems, maybe trying to find some like our own, and we're using a very unusual method using submillimeter astronomy. So if you were to look at the solar system from the outside with the submillimeter camera, you'd see very cold things like Pluto, for example, comets, and in particular you'd see the debris, the fallout of collisions of comets, which happen very rarely around our own sun, but they do happen. This produces a shower of little cold particles which emit in the submillimeter. So we couldn't actually detect an individual like large rock like the Earth, for example, but if you smashed it all up and spread it around a solar system, you'd have so much emitting surface of little rocks that then you could detect it with a camera like SCUBA.
It's like inside-out astronomy. We don't see the star, we see the cold stuff on the outside.
Exactly. It's the perfect way of picking out the cold outskirts of the solar system or another planetary system.
And of course detecting it is fun, but what you want to do is take a photo, and for that you need SCUBA.
Yeah, SCUBA was amazing. It was the first real submillimeter camera. So before that we had instruments that could measure submillimeter light, but it was almost like doing a join the dots. You get one measurement and you get another measurement and you try and build them up very slowly into a picture, whereas SCUBA just took the picture. So it was an amazing breakthrough.
Well, let's look at some examples. Why don't we start with Tor Cetus?
Yes, that was really difficult. That's the faintest thing we've done so far, but it's fascinating because it's a star that's very like the Sun, but it's actually twice as old. It's 10 billion years old. So in a way we could be peering into our own future. We wanted to look at this and see what the environment would be like. But what we found was actually really startling. It may never have been quite like the solar system because the amount of rocky particles we detect imply that around this star there's something like 20 times as many comets as there is around our Sun, even though it's a much older system. So if you were standing on a hypothetical planet around this star, you'd see comets streaking through your night sky overhead. You know, you'd be at risk of a giant meteor landing right in front of you. It would be a very dangerous place, in fact, for life to try and evolve.
When SCUBA was turned on, it very quickly made discoveries both expected and unexpected. One of the most surprising was a whole population of distant galaxies shining brightly in the submillimeter. They've become increasingly important to modern astronomy and are now called SCUBA galaxies. So, let's go back to Patrick and one of the scientists who made that crucial discovery.
We hear a lot about SCUBA galaxies. What are SCUBA galaxies?
SCUBA galaxies are very intensely star-forming galaxies. We're talking about galaxies that pump out roughly the equivalent of 1 trillion times the luminosity of the Sun. And typically they'll be forming stars at a rate of hundreds every year, massive stars that will live fast, die young, go supernova. And what we see is the energy from those hot young stars that's been absorbed by the cocoons of dust that they're born in and that they create themselves. and that dust then re-radiates that emission at a wavelength of around 100 microns, which SCUBA, observing very distant galaxies, picks up at its rest frame filter wavelength of about 850 microns.
How do you recognise a SCUBA galaxy?
Well, SCUBA galaxies aren't the prettiest galaxies in the universe when they're initially detected. They resemble nothing more than blobs, and in fact the whole science in some sense became known as blobology, because all we see is a blob on a very low resolution image. It's typically about 15 arc seconds across.
How do these SCUBA galaxies fit into the general scheme of things?
Well, it turns out, Patrick, that these SCUBA galaxies, or sub-millimeter selected galaxies, are absolutely key to our understanding of the early universe, because they represent the missing link. The local universe is known to contain large elliptical galaxies. Until now, we've never really had much of an idea of where those galaxies formed. And for many years, people have speculated where in the distant universe, where is this population? SCUBA galaxies are now believed to be that population. They form stars at a prodigious rate. They can form sufficient stars to make a large elliptical galaxy in only a few 100 million years. And therefore, and they do so almost entirely obscured from view in the optical, which explains why they haven't been found before. So they are an absolutely crucial part of the big picture of galaxy formation, and in fact the formation of galaxies, supermassive black holes, almost everything that we know to be important in the local universe.
Now, I gather that SCUBA has now come to the end of its career. Why is that?
The position it occupies on the Naismith platform of the telescope has to be cleared to make way for its successor, SCUBA 2, which is a phenomenally exciting development. SCUBA mapped 1,000 times faster than its predecessor. SCUBA 2 will map 1,000 times faster than SCUBA, and the scientific potential is almost limitless.
Well, Rob, thank you very much. Well, Chris has been in Edinburgh looking at SCUBA 2, so over now to Edinburgh.
Well, pretty though it is, Edinburgh in the winter's not quite Hawaii. But behind me are the domes of the Royal Observatory, and down below is the UK Astronomy Technology Centre. Here, they build instruments destined for telescopes all over the world. And in particular, we're here to see SCUBA 2, the world's most advanced submillimeter camera, which will end up on the JCMT.
This is SCUBA 2. This is the size of the main instrument, and this is the insides of the instrument. What you're seeing here is the section which actually houses the two arrays. The arrays themselves will be cooled down to 0.1 degree of absolute zero, minus 273 Celsius.
Wow, that's really very
That's
cold
pretty
indeed.
cold, yeah. Most of the volume here you can see is actually a cryogenic system to cool the arrays down to that very low temperature.
And those arrays, which work simultaneously, are just two cameras?
Basically, yeah, just two cameras, yeah.
And like a digital camera that you'd take off the shelf, the number of pixels is crucial.
That's right. The SCUBA 1 camera that's been working on the JCMT is 100 pixels, and that's very good going for the submillimeter. It's quite a technical challenge to build that many pixels. SCUBA 2 has something like 10,000 pixels, so that's a 2 orders of magnitude increase in the number of pixels.
And that means you can cover a much larger area of the sky.
That's right. The main emphasis behind the SCUBA 2 instrument is to do wide field surveys, from surveys of very distant high redshift galaxies to surveys of star formation in molecular clouds, and also looking at disks around nearby stars which may be forming solar systems or maybe formed solar systems. Something like 1% of the sky has been studied in any great detail in the submillimeter, and the consequence of that is we've only looked at a handful of these disks, so we don't really have any statistics about how common they are, are they really the size of our own solar system, what's going on. With SCUBA 2 what we're planning to do is look at 500 stars and hopefully detect a large percentage of disks around these stars, and then we'll be able to say something about maybe how common our solar system is around nearby stars and whether they're planets and so on.
SCUBA 2 has been on the drawing board for a long time, but work is now progressing at full speed, with the aim of having the camera on the telescope and ready for science by the end of the year. Back at the JCMT in Hawaii, work is already underway to prepare for SCUBA 2's arrival. With such a massive instrument coming, the whole structure has to be strengthened, and there's a lot still to do. Meanwhile, on the opposite side of the telescope, the other major new instrument, HARP, is ready for action. HARP is a spectrograph, splitting the radiation from the sky into its constituent wavelengths. The resulting pattern reveals the fingerprint of the chemicals which make up the object being studied. Carbon monoxide will emit radiation at one set of wavelengths, hydrogen cyanide, for example, at another set of wavelengths. With careful analysis, the shape and the intensities of these spectral lines can yield information about temperature, density, or even the movement of the gas making up the object.
This is just a great time to talk to me, Chris, because we've just got this fantastic mapping of the Orion Bright Bar, and this is the most ambitious observation we've made with the array so far. Let me show you on the screen here. What we've got here in the central screen is an image of the carbon monoxide emission from basically the M42 nebula in Orion. And here is the trapezium cluster up here. This is where it would be in the optical infrared. And down here is the bright bar. This huge, wide, very bright line. That's the gas that's been accelerated by the protostars. And then in the bar, quite a strong emission line, but a shape that varies in a very pronounced way as we move across it. And encoded in these spectra, there's vast amounts of information about the properties of the gas and what's happening in these clouds. And this is very exciting because this is the first time we made a really good picture with HARP, and it tells us that fundamentally most of the software and most of the hardware is working well.
As wonderful though it is to see the professional telescopes up on the mountain, I want to spend some time looking up at the night sky. So I've come down to the Visitors Centre, just 9,000 feet above sea level, where the public gather 365 nights a year to take part in organised star-watching sessions.
Okay, what you're looking at right there is a galaxy that is about 2 million light years away, and it is the furthest object you can see with the naked eye. Cells, and they were discovered.
Saturn was one of the first things I ever saw through a telescope, and it's rising behind me now. It's always wonderful to see people's reaction when they catch a glimpse of it through a telescope.
So you're looking at the planet Saturn? Oh man, there he is!
Wow, that's really cool.
Oh, I see the rings too.
Isn't that cool?
Up here on the summit, the quality of the sky is obvious, despite the wind. There's Castor and Pollux in the constellation of Gemini above its namesake, the 8-metre Gemini telescope. The constellation represents the twins, and there are other twins up here too, the Keck telescopes down below. Even up here at 14,000 feet, the stars twinkle because of the movement of the Earth's atmosphere. Now, if we could just keep track of that movement by watching a bright star very closely, we can correct for it, effectively putting one of these large telescopes up into space, a process known as adaptive optics. Imagine light coming from a distant object. Having travelled for thousands or even millions of years, it enters the Earth's atmosphere and is promptly ruined. The air's moving rapidly, distorting the previously perfect image. Light from a nearby bright star, though, will be distorted in exactly the same way, and so by monitoring that light, we can move a correcting mirror 50 or 100 times a second, getting rid of most of the effects from the atmosphere. Unfortunately, not every object of interest has a convenient bright star sitting right next to it, a problem astronomers have solved by firing lasers out into the night sky. The laser is tuned so that when it hits a thin layer of sodium, which happens to lie above most of the atmosphere, the sodium's excited and it glows. Light from that artificial star is distorted in just the same way as an astronomical object, and so the scientists can use that to monitor the atmosphere and remove its effects.